Hello and welcome back. Up until this point in this class, we've really kept separate the ideas of electricity and magnetism. We've basically studied these things as being two discretely separate concepts. However, most of you are probably aware that electricity and magnetism are very closely related. In fact, you've probably heard things described as being electromagnetic before. And in this video, I want to talk just a little bit about that interaction between electricity and magnetism. And in particular, I want to talk about something called electromagnetic induction, which is where changing magnetic fields can actually give rise to electric fields. And before I actually dive into this lecture, one of the things that I really just want to mention here at the beginning is that it turns out that this phenomenon that we're going to talk about is actually always present even when there aren't circuits involved. So in this lecture, we're going to talk a lot about the effect that electromagnetic induction has on circuits, how it can create currents inside circuits. But a very important concept to keep in mind is that a changing magnetic field, even if it's way out in space, far away from everything, still creates an electric field, even if that electric field has nothing to interact with, even if there are no charges that electric field will exert a force on. And that's a very, very important concept that we're going to come back to a little bit later in the year when we talk about light. Now, in order to understand the idea of electromagnetic induction, we first have to get this idea of magnetic flux. And magnetic flux is basically the same type of thing as an electric flux that we talked about when we discussed Gauss's law. And the basic idea behind magnetic flux is that it describes the amount of magnetic field that's flowing through some type of surface. And I put this in quotes, of course, because this is it's a magnetic field, so there's not like really anything that's flowing. And just like we did when we talked about the electric flux, we'll denote the magnetic flux with the capital Greek letter phi. So how do we calculate the magnetic flux? Well, the magnetic flux depends on a couple of things. It depends on the strength of the magnetic field, because of course, if you have a stronger magnetic field, there will be more magnetic field flowing through a surface. It also depends on the area of the surface. And as I mentioned before, all of our surfaces that we're going to be looking at in this video are going to be surfaces created by coils. The last thing is that it depends on the orientation of this coil. And to kind of illustrate that idea, I have these pictures down here at the bottom. And so what we're seeing is sort of a side view. If you were to look down from the top, this coil here, it's like some kind of, like a round closed surface or maybe a square or something like that, but there's some area associated with this coil. And the idea is that if this coil is perpendicular to the magnetic field, then all of the magnetic field is going to wind up flowing through this coil. So you're going to have a very large magnetic flux because you're going to have a lot of magnetic field flowing through that coil. Now, as you start to rotate this coil, you're creating a smaller effective area for that magnetic field to flow through. So for example, here we've got this really wide area, and then as I rotate it, I'm creating a shorter effective area for the magnetic field to flow through this coil. And then eventually, if I rotate the coil so that it's actually kind of parallel to the direction of these magnetic field lines, then none of these magnetic field lines are actually going to flow through this coil. And so down here we have no magnetic flux through the coil. So how do we actually calculate the magnetic flux? Well, the magnetic flux through a coil is just going to be equal to the strength of the magnetic field at the coil times the area of the coil times cosine of this angle phi. And this angle phi is the angle between the direction that's perpendicular to the surface the surface formed by the coil and the direction of the magnetic field. So for example, if this is my coil, the direction that's perpendicular to the coil points up like this. So we see we have a maximum magnetic flux when the magnetic field is parallel to the direction that's normal to the coil. So when this angle is 0, we have cosine is equal to 1, and we have a maximum magnetic flux. However, over here, when the coil is kind of parallel to these magnetic field lines, so that the direction that's normal to the coil is perpendicular to the magnetic field lines, then we have that the angle phi is 90 degrees, and so my magnetic flux is going to be 0. So let's take a look at a very simple example. And the reason I'd like to look at this example is I want to look at, well, what happens if the magnetic field doesn't fill up the entire area of a coil? So here we have two identical coils, and this coil that's over on the left, this is in an area where there's a very large magnetic field. So this magnetic field exists basically everywhere where this coil is. And on the right, I have a coil, and this coil is placed in a region where there's only a very small region of magnetic field. So hopefully you can see that this magnetic field here, this is written kind of small, but the magnetic field only exists over a region which has a radius of r halves. And the entire coil has a radius of r. So the question is how does the magnetic flux through this coil compare to the magnetic flux through the coil that's placed in a region where the magnetic field is everywhere? Well, the first thing I should point out is that because this coil is perpendicular to the direction of the magnetic field, so remember these little X's here indicate a magnetic field that's pointing into the screen. And so if we've got this coil and it's placed flat against the screen, the normal vector is either pointing into or out of the screen, and that's going to be parallel to this magnetic field. So that means my angle phi is 0 degrees, and so cosine of phi is going to be 1. So that means the magnetic flux through this coil is just going to be equal to the strength of the magnetic field times the area of the coil. In other words, it's going to be pi r squared times the strength of the magnetic field. And so that's going to be the flux through this coil. However, what happens if the magnetic field doesn't fill the entire area of the coil? So here, the magnetic field is only filling up an area that has a radius of r halves. So in this case, the magnetic flux, remember, the magnetic flux describes the amount of magnetic field flowing through this coil. So here, the amount of magnetic field flowing through this coil, well, it's only really flowing through this area of the coil. So it turns out that the magnetic flux here is going to be the magnetic field times just the area of this region through which the magnetic field is flowing. So that's going to be pi r halves squared. Or in other words, it'll be 1/4 pi r squared times b. And 1/4 because I'm squaring the half. So here we can see there's going to be a much smaller magnetic flux through this coil. So how exactly is this magnetic flux related to electricity and magnetism? Now, at the very beginning of this video, I described how changing magnetic fields can give rise to an electric field. And in particular, it turns out that when there's a changing magnetic flux through a coil, this changing magnetic flux will give rise to a voltage inside the coil. And this phenomenon is called electromagnetic induction. Now, one thing I should point out about electromagnetic induction is that for some reason, whenever we talk about the voltage that's created through electromagnetic induction, we almost always use the EMF to describe that voltage. And remember, EMF stands for electromagnetic force, and it's just the same thing as a voltage. It's just another word for the voltage. And so it turns out that the voltage that's created by a changing magnetic flux is equal to the number of turns in the coil times the rate that the magnetic flux is changing. And the reason we have the number of turns in a coil is that you could imagine wrapping a coil around in a circle, or wrapping a wire around in a circle more than once. So you could have like a coil that has like 100 turns in it or something like that. And that's very frequently done in the real world, because if we want to use electromagnetic induction to generate a voltage, we can see from this formula that if I have say 1,000 turns in a coil, then I'm going to wind up with 1,000 times larger voltage. So you can use that to generate very large voltages. Now, the direction of the voltage that's created through electromagnetic induction is given by something called Lenz's law. And basically, what Lenz's law says is that the voltage that is created through electromagnetic induction always tends to create magnetic fields which oppose the change to the magnetic flux. So the idea is that when there's a changing magnetic flux through a coil, this is going to generate a voltage in the coil. And that voltage is in turn going to generate a current that flows through the coil. and that current flowing through the coil will always generate a magnetic field that opposes the change in the magnetic flux through the coil. So how exactly does this work? Well, let's look at a couple of examples. So here I start out with a coil that is placed inside a region where there is no magnetic field. And then suddenly I'm going to turn on a magnetic field. And so this magnetic field, you can see they have these dots. That means the magnetic field is pointing out of the screen. So we're going to create a magnetic field which points out of the screen. And the question is what direction is the current that's going to be flowing through this coil? So we're going to generate some kind of voltage in this coil, and that's going to create a current that's going to flow through it. So what direction does the current flow through the coil? Well, Lenz's law tells us that the current flowing through this coil is going to tend to create a magnetic field which is going to oppose the magnetic flux. So if we suddenly create a magnetic field which is pointing out of the screen, so we're creating a magnetic flux which points out of the screen, the coil is going to want to generate a magnetic field which points into the screen, so that inside this coil, those two magnetic fields are going to cancel out, so that we're opposing the change to the magnetic flux through the coil, because the coil started out with no magnetic flux through it. It wants to keep it that way, so it's going to oppose this change to the magnetic flux by creating a magnetic field that points in the opposite direction. So remember that the magnetic field that is created by a current-carrying loop is given by this right-hand rule, so that if you curl your fingers in your right hand in the direction that the current is flowing through a loop, your thumb will point in the direction of the magnetic field. Now here, we said that we want this magnetic field to point into the screen so that it's going to cancel the magnetic field that is pointing out of the screen. So in order for that to happen, right, if I point the thumb on my right hand into the screen, I can see that my fingers on my right hand are going to curl in a clockwise direction. So that means that the voltage that's induced inside this coil is going to tend to create currents which are going to flow in this clockwise direction. That way, the current that's being induced inside this coil will generate its own magnetic field, which is going to point into the screen and help cancel this increase in the magnetic field that's pointing out of the screen. So that way, it'll kind of keep things the way they originally were. So let's take a look at another simple example. And in this example, we again start out with a coil which is in a region where there is no magnetic field. And then we're going to suddenly turn on a magnetic field which points into the screen. So when we do this, we are going to increase the magnetic flux which is flowing into this coil. Okay? And remember that Lenz's law tells us that the coil is going to tend to create a magnetic field which opposes the change in the magnetic flux. So here we've increased the magnetic flux that's going into the coil by turning on this magnetic field. So the magnetic field is going to want to oppose that by creating a magnetic field which points out of the screen so that it cancels this magnetic field that we've created. So remember that the right-hand rule says that the magnetic field points in the direction that your thumb points on your right hand. So we want this magnetic field to point out of the screen. So if I point my right hand so my thumb points away from the screen, the fingers on my hand are going to curl in a counterclockwise direction. So that means the current flowing through this coil is going to flow in a counterclockwise direction. Now let's look at another similar example. I actually don't have in the slideshow, but I think it's an important thing to point out. So what happens if I have a coil that was initially in a region with a magnetic field? So let's say it starts out in a region where this magnetic field that points into the screen. And then let's say I suddenly pull on this coil and I remove it from this region. So now I'm going to move it into a region where there's no magnetic field. And the question is, well, what direction does the current flow through this coil? Well, initially here, we're going to start out now with a magnetic flux flowing through the coil. So we're starting out with a magnetic flux that's flowing into the coil. And remember that Lenz's law tells us that the current that's induced inside a coil always opposes the change to the magnetic flux. So if we start out with a magnetic flux that points into the screen, the coil is going to want to keep it that way. So if we pull the coil into a region where there's no magnetic field, the coil is going to want to generate its own magnetic field pointing into the screen so that it maintains that magnetic flux that pointed into the screen. So in order to do this, the current flowing through the coil is going to have to flow clockwise through this coil, right? Again, we can see that because we're looking for a magnetic field that's going to point into the screen. So if I point the thumb on my right hand into the screen, then the fingers on my hand are going to rotate or curl around in a sort of clockwise fashion. And that's going to be the direction that the current will flow through this coil. So let's take a look at a somewhat more quantitative example. And this example asks us to find the average voltage that's induced inside the loop below during the 6-second interval starting when the rod passes point A. So in the figure below, we have these two wires which are coming together at this point A, and they're at an angle of 19 degrees. And then connecting these two wires is this metal rod, which is sliding to the right at a speed of 0.6 meters per second. And the idea is that these two wires, along with this metal rod, are going to enclose a triangular region. And because the area of this triangular region changes as the metal rod moves towards the right, the magnetic flux through this triangular region is always going to be changing, and that's going to induce a voltage in this triangular circuit. And I forgot to write, the magnetic field inside this area is equal to 0.38 Tesla. So hopefully you can see there are these X's here that denotes a magnetic field which is pointing into the screen. And actually, before we even get into calculating this voltage, let's consider applying Lenz's law to find the direction of the current. So here, as this metal rod moves towards the right, it's increasing this area. So it's going to increase the magnetic flux which is flowing into the screen. And because Lenz's law tells us that the coil induced inside any circuit is always going to oppose the changing magnetic flux, because this rod moving towards the right is going to create an increasing magnetic flux which points into the screen, the current flowing through this is going to tend to create a magnetic field which points out of the screen, so that it cancels that increasing magnetic flux that points into the screen. And in order to have a magnetic field which points out of the screen, the current is going to have to flow through this triangular circuit in a counterclockwise fashion. So our current is going to kind of flow like this. So remember that the induced voltage inside a coil, this EMF, is equal to the number of turns in the coil times the rate that the magnetic flux is changing. And in this case, because we just have a single loop of wire, the N here is just going to equal 1. So the change in the magnetic flux is going to be equal to the induced voltage. So all we really need to do is calculate the change in the magnetic flux. Now initially, this copper rod is going to start out really over here at this point A. So when this rod is over here at this point A, it's really not enclosing any type of area. So the initial flux is just going to be equal to 0 Tesla meters squared. And it's going to be units of Tesla meters squared, remember, because it's the strength of the magnetic field times an area. Now, once the coil has moved to the right for 6 seconds, so if the rod moves towards the right at a speed of 0.6 meters per second for 6 seconds, then it's going to move to the right a distance that's equal to V delta T. So that's going to be 0.6 meters per second times 6 seconds, and that's 3.6 meters. So here we're going to have these two wires. They form a 19-degree angle, and they're going to be connected together by this rod. And this rod is going to have moved to the right by 3.6 meters. Now, the magnetic flux through this is just going to be equal to the strength of the magnetic field times the area that's enclosed by these two wires and this metal rod. And because the magnetic field is perpendicular to the area here, the magnetic flux is just going to be BA, because this cosine of phi, this is going to be equal to 1. So we have the strength of the magnetic field times the area of this triangle. Remember, the area of a triangle is 1/2 times the length of the base, which is 3.6 meters, times the height of the triangle. And we haven't really been told the height of the triangle, but we know that this angle here is 13 degrees. So this height over here we can use trigonometry to find, so h. So if we look at this, I need to relate the opposite side to the adjacent side, and the way we do that is with tangent. So tangent of 19 degrees is going to equal h divided by 3.6 meters, or h divided by v delta t. So h is going to equal v delta t times tangent of 19 degrees. So the flux is going to be equal to 1/2 times the base, which is v delta t, times the height, which is going to equal v delta t times tangent of 19 degrees. And then all of this is the area of that triangle, so we're going to multiply all of that by the magnetic field to get the magnetic flux. And remember, the induced voltage is the rate that the magnetic flux is changing, right? So this is equal to the rate that the magnetic flux changes. So it's going to equal the final flux minus the initial flux divided by delta t. But my initial flux was equal to 0, so it's just the final magnetic flux divided by delta t. And my final magnetic flux is going to be equal to, so we had a 1/2 times, really we had a v delta t squared, if we think about this, because I have that term in here twice, times tangent of 19 degrees, and then all of this times the magnetic field, and now I have to divide this by the time delta t to get the rate that the magnetic flux is changing. So that dividing it by delta t is going to cancel one of these delta t's in the numerator, and we'll have 1/2 v squared. Let me go ahead and write this as b times delta t times tangent of 19 degrees. And if I plug all these numbers into a calculator, let's see, I think I should get 0.14 volts. So that's the voltage, that's the average voltage that's induced during the first 6 seconds. Now, one thing I should probably point out about this is that that just gives us the average voltage that was induced. Actually, what's going to happen is that as that rod moves to the right, the voltage that's induced is actually going to be changing, and we could calculate the actual instantaneous voltage that's induced by taking a derivative and using calculus. But this just gives us the average voltage that's induced during that first 6 seconds. So another phenomenon which I'd like to talk about is something called motional EMF. And the basic idea behind motional EMF is that it turns out that if you take a metal rod and you move this metal rod through a region where there's a magnetic field, this is actually going to induce a voltage difference between the two ends of the metal rod. And so I want to start out with a familiar example. So in this example, we have this metal wire, which kind of forms this open sort of rectangular region, and then we have this metal rod, which is going to close off this rectangular region. So this is going to enclose a rectangular region, and this metal rod is moving towards the right with some velocity v. And so as this metal rod moves towards the right, it's going to increase this area that's enclosing a magnetic field. So that's going to increase the magnetic flux through this rectangular region as this metal rod moves towards the right. And so the first question I want to ask is, well, what is the voltage that's going to be induced inside this loop? It's caused by this metal rod moving towards the right. Now remember, the induced voltage is equal to N times the rate that the flux changes. And in this case, N is just going to be equal to 1. So here we have the rate that the flux changes, and the flux in this case is just going to be equal to the strength of the magnetic field times the area enclosed by this wire and this metal rod. We're dividing this again by delta t. And the rate that this area is changing, this is going to be equal to, so the area is equal to, let me call this L, this is the length of the rod, and we'll call this over here, this is delta x, this is the width of this region that's enclosed. So this area is going to be equal to L times delta x, and the rate this changes is going to be that divided by delta t. And so if we rewrite this slightly, I could rewrite this as BL times delta x over delta t. But of course, delta x over delta t is just equal to the velocity that this rod is moving. So this is going to equal BLV. And one thing I want to point out about this formula, which we just found, is that this formula only depends on the properties of this metal rod, which is moving to the right. It depends on the strength of the magnetic field, the length of this rod, and the velocity of the rod. It doesn't depend on this, this copper, or whatever this wire is, which is enclosing this area. And it turns out that, in fact, anytime you have a metal rod which is moving perpendicular to a magnetic field, you will always induce a voltage which is given by this formula. And so to understand why this happens, let's consider what happens when I have a metal rod just moving in a region with a magnetic field. So now we're not really enclosing this with any other circuit. We just have a metal rod moving perpendicular to a magnetic field. Now, remember that I've described metal objects before as being kind of like containers that are just holding this electron gas that can kind of move around wherever it wants. So if I have this metal rod and it's moving towards the right, then all of the little electrons inside this metal are also forced to move to the right because they're trapped inside this metal. So all of these electrons have this average velocity which is pointing towards the right. And so, because these electrons are in a region where there's a magnetic field, the magnetic field is going to generally exert a force on these electrons. So we can calculate the direction of that force. So remember that because electrons are negatively charged, they're going to point in the opposite direction that we get from using the right-hand rule. And remember, we use the right-hand rule by first pointing your hand in the direction of the velocity. So you want to point your right hand so your fingers point towards the right side of the screen. And then you want to orient your hand so that when you curl your fingers curl into the direction of the magnetic field. Now here we have these little X's here for the magnetic field. That means the magnetic field is pointing into the screen. So if I orient my right hand so that my fingers point initially to the right side of the screen, and then when I curl the fingers on my hand, they point into the screen, I see that my thumb points towards the top of the screen. So if we had positively charged particles, they'd be experiencing a force which points towards the top of the screen. But because electrons are negatively charged, they experience a magnetic force which points towards the bottom of the screen. So what happens is that all of these electrons inside this metal rod are experiencing a magnetic force which tends to push them towards the bottom of the rod. And what this does is it causes a negative charge to slowly start to build up on the bottom of the rod, leaving behind a positive charge on the top of the rod. However, this type of charge distribution inside the metal is going to give rise to an electric field, right? So there's going to be this electric field which is going to point from this positive charged towards this negatively charged end. And this electric field itself is going to oppose the motion of the electrons that are moving downwards due to this magnetic force. Right? So the basic idea is that this magnetic force is forcing a whole bunch of electrons towards the bottom of this rod. But as electrons accumulate in the bottom portion of this rod, it's going to create a repulsive force which is going to oppose the motion of electrons towards the bottom part of the rod. And so eventually this whole thing is going to reach equilibrium when the magnetic force, which is pushing the electrons towards the bottom of the rod, is canceled out by the electrostatic force caused by the collection of the negative charge on the bottom of the rod and the positive charge on the top of the rod. So equilibrium will be established when the electrostatic force is equal to the magnetic force. And the electrostatic force is given by Q times the electric field inside that rod, and the magnetic force is given by QVB. So we can see the Q's are going to cancel, so the strength of the electric field inside this rod is going to equal Q times B. Now remember that the voltage difference between 2 points is equal to the strength of the electric field times the displacement that's parallel to that electric field. So if I calculate the voltage difference between the top end and the bottom end of the rod, that's just going to equal the strength of this electric field times the length of the rod. So I see the voltage difference between the two ends of the rod is just going to equal E times the length of the rod, and that's going to equal VBL. Notice that that is exactly the same formula which we found for the voltage difference for that metal rod which was connecting this rectangular circuit. So here we found that voltage was BLV, and here we have the same thing. It's going to be BLV. And the last thing that I really want to mention about electromagnetic induction is that this is really probably one of the most useful phenomena that we're going to talk about in this class. And the reason is that electromagnetic induction is the basic phenomenon which is used inside power plants to generate electricity. So the idea is that you hook up a turbine to a permanent magnet which is placed inside the coil, so that that permanent magnet is going to go spinning around in circles inside the coil. And that's going to create a changing magnetic field in the coil. So this magnetic field vector is constantly going to be rotating around, and that magnetic field through this coil is constantly going to be changing direction. So that's going to create a changing magnetic flux through this very large coil, and that's going to in turn generate a alternating voltage. And so that's actually why, if you've ever looked at the voltage that's created by like the power sockets in your house, if you plot that voltage versus time, it's going up and down like this. And the reason is that the magnetic flux that's going through this coil, that's equal to BA cosine of phi, and this angle phi here is always changing, right? As this magnet rotates, this angle is going to also be changing in time. So what you're creating is you're creating this alternating voltage, and that's actually how we generate electricity inside a power plant. And so at this point, I think I'd like to end our discussion on electromagnetic induction, and in the next video, I'm going to talk about how energy is still conserved even with electromagnetic induction. And this is something I think is really cool, how we can see energy conservation between like mechanical things like gravity and circuits. So for example, what if I had a gravity-powered circuit? We'll be able to see that energy is still going to be conserved.